So, then welcome to, I don't actually know what is the number of this lecture, but it's it's a part of the CFD lecture, of course, and it's a mini series in itself, in as much as we discuss here what we call the kinetic, which is not really a word, but we call this kinetic fluid dynamics in comparison to computational fluid dynamics. So this course will use the virtual fluid software, and the virtual fluid software is not a classical CFD software, but it is using the Lattice Boltzmann method, and for this reason there will be, I approximate now, 3 lectures introducing the concepts that we need for understanding what the Lattice Boltzmann method is about. Yeah. So just I wrote down here what computational fluid dynamics in principle is. So we do, of course, numerical approximation. What is a fluid? It's a very good question for your PhD defense, that somebody asks whether you get the very basics. Yeah, it's a fluid is a substance that deforms arbitrarily under arbitrarily small forces. That's a fluid. Of course, only arbitrarily if you wait long enough. Yeah, but otherwise there's no lower bound on the force that leads to, no movement. Yeah, and then we are interested basically in not only in the pressure field, but also in the velocity field. That makes things dynamic. It's not always the case that there is, dynamics does not necessarily mean that the velocity field is also changing in time, even though this is what we are mainly studying here. But it could also be that the velocity field itself is kind of static, but then it's still dynamics because something is moving around. Okay, so now there is, why am I talking about kinetic fluid, what we call here kinetic fluid dynamics? So there are different ways how you can model or describe the universe, and with regard to fluid dynamics, there are mainly, so there's always one that you forget potentially, but there are mainly 3 ways how you can describe this phenomenon or the system. There is, of course, the atomistic picture of the world. So in the atomistic picture of the world, you could say there are kind of molecules or atoms that are flying about. So I'm going to draw them like this, and then there are forces, so playing around with equations. There will be an acceleration of a particle I that has the mass I is given as the sum over all interactions with other forces, particles. Yeah, so this is simply, you could say, Newton's law. Yeah. So acceleration of one particle depends on the forces that act on this. So this is the atomistic view. That is where you can describe your fluid, and you can also simulate your fluid. This is then done with you say molecular dynamics. And in molecular dynamics, we are interested in the individual particles or molecules, say molecules. So this is, you could say, one end of the spectrum, and then on the other end of the spectrum, there is, which, because of I'm lacking a better word, I describe it as continuous, even though it's not the only continuous approach. So continuous, say there is an object and you describe somehow the flow field in terms of, for example, these streamlines around this, and this you describe, playing again with equations, with the Navier-Stokes equation that Hussein also introduced. So this would basically look like this. There's a change in the velocity u that is produced through an advection term, which is the one here still on the left-hand side, and then there is a gradient in pressure, and then there is a diffusion term that can be written in different ways, but we write it as nu, which is the kinematic viscosity times this Laplace operator second derivative of u. I think this is Hussein has talked about this. So, and then in the middle, if you will, there is what we call the kinetic description, and the kinetic description. Okay, I should say here no molecules. I mean, historically, I should not talk too much about history, but historically, you know, the Navier-Stokes equation, I mean, it was found 3 times, once by Navier, once by Stokes, and once by Bernoulli. And Bernoulli they forgot because he was the first one, actually. So this was in the early 19th century. And if you know about something about the history of science, then the 19th century was the time when many of these differential equations were discovered. And during that time, it was very uncommon to assume, or it was actually not, it was considered unscientific to assume that matter is discontinuous. I mean, you could just, they've just discovered that there is this infinitesimal calculation, yeah, and this all requires, of course, that your fields are continuous, because you take a derivative of them. And the atomic hypothesis, this was, of course, known, because this was this is how the ancient civilizations assumed the universe to function, that there are atoms, yeah. And so in the 19th century, if you were talking about atoms, you were basically something like a flat earther, yeah. So in this time, this was considered the truth, and there would be no molecules. Yeah, I mean, they did not. The guys who worked and invented the Navier-Stokes equations, they definitely did not believe in molecules. Yeah. So now, I guess you believe in molecules, just because somebody told you, yeah, that this is the case, and strangely enough, we still believe in these differential equations. So we have you know, there is this kind of discrepancy that I find funny that actually nobody really questions. Yeah? So you have the atoms and you have the differential equations, and both exist and both somehow work. And so how do they get actually together? There is a whole field of physics that engineers don't care a lot about, and this is the kinetic, the physical kinetics, which is not to be confused with mechanical kinetics. Yeah. So if you look at Landau-Lifshitz, do you know Landau-Lifshitz? Probably not. No, Landau-Lifshitz is a standard. Landau-Lifshitz are two physicists, Russian physicists, of course, but they wrote a series of books. Yeah, and this is so. When you say Landau-Lifshitz, you are referring to these books, and you see them sometimes cited also in scientific literature, because they are considered the standard textbook for physics. So this is a book where you can, I mean, if you talk about standard physics, you usually refer to this book because everybody says that this is the best book describing this. So there's the first volume is mechanics, yeah, and the 11th, the last volume, is physical kinetics. So usually engineers don't arrive there, but the physical kinetics is the theory that actually connects the atomistic worldview with the continuous worldview. Yeah? So here you see why both worlds actually work together. So what happens in this in this kinetic worldview? So what you have is a distribution function. We'll come to what that means in a minute, or in a few more minutes. So this is a probability. Is a probability of finding particles. Yeah. So and then there is a particle velocity, and the particles are somehow distributed, statistically distributed in this velocity space, and this usually looks a little bit like a Gaussian function, and they are centered around the velocity that then becomes the continuous variable. So this is the statistics of molecules. So you see, this is something in between. I mean, or not actually in between, but it is describing molecules on the one hand, but on the other hand, it is still continuous because it's not describing the actual molecules themselves, but only the probability of them being somewhere. Yeah. So, and for this we also have an equation, and this is the Boltzmann equation, which is the thing that we are going to solve. This looks like this. There's a change in time of the probability distribution. Then there is something that looks similar to this term here. It's also called an advection term. And then there is on the other side something that's called the collision term. So this is called the Boltzmann equation. So we have these three descriptions of our world, and usually most CFD software works in this context, because this is enough. This here keeps more information, so this can become more complicated. And this is used for very special things, like you have vehicles re-entering the space vehicles re-entering the atmosphere or so, then you need to use this equation. If you don't want to use this equation, you can always use this one. It's just too expensive. And what we do with Lattice Boltzmann is, you could say, we are kind of a bit in between these two, but we are built on this equation. Okay. So let's just that I have it on the recording. These strange faces. This is my stupid, childish way of, this is your virtual tutor. This one is called Nabla. It's the operator that tells you something, and then we have the Laplace operator. This I always indicate as asking questions. Yeah. So if you want to know what these things mean. So CFD is most CFD is done with the continuous. I'm dyslexic, so I always have to look at my script, and I will make mistakes anyway. Just if you can't read it, just ask. Yeah. So we do something else. We use the kinetic. Approach, and this is what we now try to understand. Let's say I call this now kinetic fluid dynamics. KFD, if you will. Yeah. And it somehow sounds like you want to eat chicken, and So, anyway, try to understand what this means and how this is different from the other approaches. So, there is a state space that we have to consider, and this state space is the spatial, the location. It's always strange to say spatial space. This is just what we usually consider to be space, yeah? But we have to name it because we have, in addition to this, we have the velocity space. So you see, these are then six independent variables instead of the usual 3, but this is not necessarily all of this. There's also, in principle, but this is not what I put it in brackets because we are not using this. If we have molecules that have internal degrees of freedom, these internal degrees of freedom are additional dimensions of the problem. So they can have vibrations and they can have rotations. And these will make up additional degrees of, not additional degrees of freedom, but additional dimensions of the problem. So, but in our case, we'll skip over them because we'll simplify it a little bit. So we have X, Y, and Z. So this is what we usually have as spatial space. And then we have these ugly things that is Xi. Xi is a microscopic molecular velocity, Xi, and they have, out of this, they have 3 types. So this is the velocity. And it's always important to distinguish between this, because this is the velocity of the molecule, which is not the velocity of the fluid. Yeah? So it's not the continuous velocity field, but it's the velocity of a single molecule. So, and now, okay, I have to put a little bit of text here as explanation. Let me write this. So, a molecule is said to be in state X, Y, C, X, Y, Z, if it is at position X, Y, and Z, and has velocity Cx, Cy, and Cz. Okay, then it is in this state. So, and now we say that if a molecule so this is kind of a little bit nomenclature now. If a molecule exists in a certain state, the state is said to be occupied. Okay, so there are different statistics concerning whether a state can be occupied by one or by many particles. So usually the velocity state itself could be occupied by many particles, but the position of usual particles can only be occupied by one particle. So that would mean that this is an exclusive statistic. So if one state is occupied, there cannot be another particle in the same state. So then what is the actual probability? Now you need to know a little bit about statistics to understand this. Yeah, I hope you may have had this previously, some statistics. If not, okay, we don't need a lot. So the probability density is actually inversely defined through an integral, namely that the integral over the density, so f, what the f that we had previously is a density. So this gives us P, which is not the pressure, this is a capital P here. So if we integrate x1, x2, and y1, y2, and z1 to z2, so this would be the integral over space. Yeah, and then we go on and integrate also over velocity space, xi x1 and xi x2, xi y1 and xi y2. Sorry for all these integrals. Z1 and xi z2. This is not the largest number of integrals that we sometimes need for doing this. So we have a probability density f, and we integrate this over xi z, y, x, And so what was the order? That y x. So this integral is the probability of finding a molecule in the state volume. So, okay, not in that particular one state, but in the volume of this state over which the integral is taken. So this is this density, and this is the thing that we want to describe. So why is this a good idea to do it this way? I mean, compared to molecular dynamics. Let me try to explain. So the kinetic theory describes, in this case, a fluid, but this also can be done for solids or whatever, electrons or whatever. So we describe this from the perspective of the phase space it occupies. And because we are in a classroom, I always try to explain this with a classroom. Yeah. So I'm not using your names. I'm using other names. Say this is my classroom. Yeah. And here there's so the classroom has seats somehow. And on these seats there is, for example, Monica here, then there is Mike there, and there is Marvin here. I like names that start with M. So this is in particular if you have few people in the classroom, then this would be a good description of your classroom, right? But suppose you have many. Then you can also see this in a different way. So say there are these seats again, and all we say now is that this seat is occupied, this seat is occupied, and that seat is occupied. Yeah? So these are two models of the same thing. But you see, there is a difference. So first of all, when you have only this description, you don't know that there's actually Monica here today, yeah, and you don't know that Monica sits in this corner, so she could also sit there. So while describing the same thing, this here contains much more information than that here. And whether this is good or bad obviously depends on whether you are interested in this information or not. If you are not interested in this information, you definitely don't want to know this, in particular, if there is very, very many things that you would describe. And if you describe a fluid, yeah, like you have like a small glass of water, then you would have 10 by the power of 24, because this thing's 5 mole or something, 10 by the power of 24 or 25 molecules in this one glass of water. So you don't want to distinguish them by name, okay? So this is here the big difference. So there is no distinction between individuals. Meaning that you have a substantial reduction of information which modeling people like. So, I mean, now we don't need to, since we don't need to name them, yeah, we just have the statistic and we can deal with very, very many particles. Of particles or molecules. So, okay, one thing I like to, because there are sometimes misunderstandings, so I like to write this down, that this, what we call kinetic, this has no relationship to what in mechanics, you know, we have a lot of civil engineers running around here. You may not be one, but they have a clear understanding what they believe is kinetics, yeah, because they come from mechanics. But the word kinetic can mean different things, and basically what actually kinetic means, what all the definitions have in common is that they describe changes between states. Yeah, this is what they have in common, but otherwise they mean very, very different things. So kinetic has no relation to mechanical, to the mechanical kinetics. I don't like the word, but I cannot change physics, right? I mean, this is the name that was given to it. So what this refers to is the change of the states, the dynamics of the states. Basically, the transitions from one occupied state to another. Okay, all of this is described by the Boltzmann transport equation. And by the way, you can do computational fluid dynamics or fluid dynamics in general for your entire life, and you have never heard about the Boltzmann equation, yeah? So then, but here we are using the Boltzmann equation. I'm writing it again. So the Boltzmann equation is the time derivative of this probability density F together with the advection of the same thing with the molecular velocity xi scalar product on the gradient, okay, on nabla, and this, okay, this forms a new operator. This is an advection operator. And on the other side, we have a collision that acts on a binary collision operator. Yeah. So this here is the change in time. So this is a linear advection operator. The linear advection operator is a big advantage of the Boltzmann equation over the Navier-Stokes equation, because in the Navier-Stokes equation this operator is nonlinear. And this here is a binary collision. Well, operator is a little bit lazy word, because an operator usually acts on something. So you could, maybe it's mathematically more accurate to say this is a collision term than an operator, yeah, but it takes in as a function this probability distribution, and it takes it in twice, because it needs two particles to have a collision.
It's like a domain.
Domain?
This operator, like this one, omega or something, is not like in most of the time say like the domain -1 to 0 or something like that.
No, usually, okay, so this here is an operator because it acts on F. This here also is an operator because it acts on F, but this here, you see, the F is inside. So you could potentially rewrite this as another thing that depends on F and that acts on F. But this is usually not the way it is written here. But it acts on F, but it's written in a different way. This is a little bit lazy mathematics. You know, all of this has a lot of history behind it, and if we reinvented it, we would probably write it a little bit different. In particular, we wouldn't call it kinetics, yeah, because this leads to a lot of confusion. So let's try to understand these terms. I'm not describing what dt f means. This is the change in time, but I'll describe the advection as the state transition due to molecular velocity xi. So this is what we call advection. So there's a very simple picture that you can, so there's a position x, yeah? And here is the velocity in that particular direction. And now if we take any shape in this space that looks like this and say this is at time equals to 0, then at a later time, t is equal to t1, yeah? So these things basically have moved. So if a molecule, saying that if a molecule is at this position x and has a velocity cx, so say this position here, then after a given time it will end up here. Yeah? So, and you know, the more velocity it had, the further it has moved, obviously. So this is pretty straightforward. Molecules move in the direction of their velocity, and this is what the advection operator on the left-hand side actually describes. So this is simple. Then there is something that is actually not simple, and this is the state change due to collision. And we only describe binary collision here. So there's already an assumption in this binary collision. We assume that the fluid is kind of a little bit dilute, such that it is extremely uncommon that more than two particles will directly collide at the same time. Yeah? So there's only, this is where we describe only binary collisions, and then you can think about when actually three particles meet at the same time, whether you can describe this as a series of two collisions. Yeah? So they meet in arbitrarily small time instance, and that even if three cars collide on the street, they usually collide after each other and not all at the same time. Yeah. So this is why we have only binary collisions. So what is actually happening when molecules or molecules that are coming close enough to each other collide. So, and when they collide, they usually don't break apart. So this could also happen, but this would only happen if they collided at very, very high velocity, which is not what we consider here. But here we consider that they exchange energy and momentum by any forces that are acting on them. So they exchange energy and momentum, and now important is that these two things are conserved quantities in the collision. So the sum of energy and momentum is conserved in the collision. So we can draw a picture like this, which is part of the state space. Well, state space has 6 dimensions, so we cannot easily draw all of this, but we can draw part of this. And this part here is saying this is Xx, and I shift this by Ux. And this here is Xy minus Uy. And by the way, since there are two particles colliding, we can always define a plane in which they are colliding. Yeah? So they are, of course, not necessarily the xy plane, but we can always turn things such that they collide inside a plane. Yeah? So coming in the plane and going out the plane. Of course, only after the collision we know what this plane looks like. Yeah? But anyway, they will always be in a plane. And So what I've done here is I subtract from the molecular velocity, I subtract the average velocities of the two particles colliding. So this is C1, the one particle coming in, plus the other particle coming in, divided by 2. So we look at the centered velocity, and I put my 0 like here, and now we consider two particles. So because they two particles coming in like this, saying this here would be C1 and this here would be C2, and then they go out in another direction like this, and say this here would be C1 after the collision, which I C2 after the collision, and they will be, even if this is not very nicely drawn here, but they will be on a circle in this picture. Yeah. So if the length of the vector is the velocity. Yeah. So because the length, the sum of the lengths of these vectors has to be conserved, because this is giving you the energy. Yeah? So the center has to be conserved, and the length of the vectors have to be conserved. The center is the momentum, and the radius is the energy. Okay, now how this happens that particles collide, this is of course very, very, very complicated, but then Boltzmann had this interesting idea that comes by the German name Stoßzahlenansatz, which is written with a scharfes S, so that everybody around the world has to use this word. Actually, this is a Stoßzahlenansatz is also sometimes used in English, but they decided to translate this into molecular chaos. Or molecular chaos assumption. I think that Stoßzahlenansatz and molecular chaos sound very, very different, right? But they are supposed to describe the same thing. I think chaos had a different meaning in the time of Boltzmann. Yeah, they were not. He was not talking about chaos theory in this time. This came 100 years later. So Stoßzahlansatz, yeah, Stoßzahlansatz basically is the number of the ansatz of the number of collisions, yeah, and I think this describes it. I mean, this is really the source. So Boltzmann thought about this, and this was his thinking. You can now say a lot on how particles collide, what forces are they acting on, and so on. But actually, he said, so forget all about this. We only count how many particles are actually colliding. Yeah. So this is all we care about. Yeah. So everything is about reduction of information. Yeah. I mean, we are not interested in this detail. We just count how many collisions there are. And so this, and see whether this actually describes our behavior, and it actually does. So the macroscopic behavior depends only on the number of binary collisions. in a given volume over a given time. Okay, so this is a drastic simplification. So how did anybody? Okay, small step back, because when I look at my script, I see that I should probably explain one small detail here. Yeah. So how does anybody come up with translating Stoßzahlenansatz to molecular chaos? There's a small emphasis on two different aspects of Boltzmann's idea. Because Boltzmann had to make one additional assumption here, namely that the molecules do not remember their previous paths. His assumption was basically that the two particles are not correlated to each other. So the problem is the following. You have the particle, you don't know the particles, you only know their statistical distribution. So and now when particles collide, you would pick one particle out of the statistical distribution, and you pick another one out of this statistical distribution. Say you pick the one first and the other one later. So now basically, if you pick one particle out of a distribution, then you have changed the distribution. Yeah? So say you're throwing dice. You're throwing two dice, and you know the number that you've thrown is 7. Yeah? So now you pick one of the dice and say, this has the number 3. Then you automatically know the other one. So putting one out of this, taking one out of the distribution makes the rest dependent on it, right? So, but the assumption here is that there is not one dice, but many dice. And so many dice actually, that the distribution does not change when you pick one of the dice, right? So this is an important assumption that you have to do. It's not true. It's not true if there's just 2 or 3 particles. Yeah, but since there are so many particles, it is true. Okay, and this is basically when they translated this, they focused on this different aspect of this idea. Okay, now here comes my Laplace operator. How many collisions are there? So this depends on on the physics of your particles, how they are built, how large they are, and how heavy they are. But all of this can be reduced to just 2 numbers. One of them is the mean time between collisions. Now think about it like this. We have a particle flying about here, and here's another particle, and they will collide here, say, yeah? So then one of them will change their direction and will end up here. And here's the next time somebody is coming and they have the next collision. Okay? So then there obviously is a distance traveled between these collisions that we call lambda, and this distance is covered in a certain time. So because the particle has a certain velocity, and this velocity is termed the VTH for thermal velocity. So this lambda is the mean free time. So you see everything is statistically here. Oh, sorry, there's no time. Path. The mean free path. Then there is a thermal velocity. So this thermal velocity is up to constant of order 1, as you say, the speed of sound. I mean, this is very convenient because this can be very easily measured, this thing. And then there is the mean free time. So the mean free time, basically, tau is very obviously the distance traveled by the velocity. This is the mean free time. So, and now this, if you make the statistics, which we, not the statistics. If you do an asymptotic analysis of this Boltzmann equation, which is called the Chapman-Xcock expansion, then you see that this can be, this leads to a macroscopic behavior, or that you can asymptotically describe this with the Navier-Stokes equation. So the Navier-Stokes equation follows from the Boltzmann equation under the assumption that, so basically it's a Taylor expansion in this thing, but only to first order. Yeah? So dTu, so the time change in the average velocity, the average between the particles. Here you get this nonlinear advection operator. It's nonlinear because it has the velocity-dependent variable that you're looking for u twice in it. Here we have minus rho, and then there's something that's the density that's dropping out, and here you get this kinematic viscosity and the diffusion term for the velocity. So this here, you may know the dynamic viscosity. This is the kinematic viscosity. Kinematic. So physicists like this more because it's a proper diffusion. It's a proper diffusion coefficient. Diffusion has the units meter square by second, right? It's not Pascal seconds, this thing. And basically, actually, you see this thing here is the only parameter in the incompressible Navier-Stokes equation that actually describes the nature of the fluid. Yeah, so there is only one parameter in it, right? So then the thing cannot depend on a lot of different things because there's only one parameter. So this is the parameter describing the behavior. So my dyslexia behavior, American English, behavior of the fluid. And this thing can be identified as the terminal velocity times the mean free path, which can also be written as the mean free time times the terminal velocity square. Yeah, and by the way, depending on how well you know the German language, you may be able to read Einstein's paper about the Brownian motion in its original form, which actually describes this discovery, even though he says it's just an assumption, but later, I mean, this is true, yeah, that by measuring the viscosity that can be easily measured, and the speed of sound, the terminal velocity can also be easily measured, you can determine the mean free path and the mean free time through these equations, and that this actually implies, that when there is a viscosity, there is a finite mean free time or finite mean free path. Because if there's, if there's no, if this is, say, the particles would be infinitely close together, yeah, so then this here would be zero, so this here would disappear. So Einstein's ingenuity, and this is something nobody talks about because he did so many other famous things, but actually what he did in this other paper from 1905, and now you have to, this is the instance where the shift came from continuous physics to molecular physics, yeah, because he basically said that if there is a viscosity, then there must be molecules, because you cannot explain this otherwise, yeah. So that you observe macroscopically, that you observe diffusion means there need to be molecules. Okay, little bit of text. So viscosity is a function of the mean free time and the speed of sound. And also now you see that in order to describe this on the Navier-Stokes level, this is all we need. We only need the speed of sound and the mean free time. The Navier-Stokes equation comes, of course, out as a statistical asymptotic result from the Boltzmann equation, and it is only true for large enough systems, and this means length scales, for length scales where L, so this is the length scale on which I describe my problem, and this length scale has to be much larger than lambda, and this is described by something that we call the Knudsen number. So the Knudsen number is lambda, the mean free path, divided by the size of the system. So, and the limit in which you derive the Navier-Stokes equation. So if you're interested in actually doing this, you can come to my lecture in the winter term. There I really do the derivation. So the Knudsen number squared, this has to go to 0. So if Knudsen number squared is going to 0, then the Boltzmann equation implies the Navier-Stokes equation, which also means that this is true only, for the case that this L is much larger. So this here has to be much smaller than 1 in order for this to be true. So meaning that the Navier-Stokes equation is a first order in Knudsen approximation to the Boltzmann equation. Okay, so for a physicist, the Navier-Stokes equation is an engineering model, right? So there is no truth in the Navier-Stokes equation, and there is this Millennium project where you are asked to prove that the Navier-Stokes equation has stable solution anyway. Yeah. So if it turns out that the Navier-Stokes equation has no stable solution, then this is a mathematical problem. Physicists don't care, because from a physical point of view, we already know that the Navier-Stokes equation is wrong. Yeah? That the Navier-Stokes equation is wrong, but it gives very good approximations for a wide range of problems. Yeah? But also, we absolutely know that it is wrong, because, for example, it predicts that when a raindrop drops into the ocean, this raindrop will bounce off forever and will never merge with the ocean. If you solve the Navier-Stokes equation for this problem, this is the outcome. Yeah? It is impossible for two separate fluid parcels to touch in the Navier-Stokes equation. And the only reason why they do, in reality, is because the Navier-Stokes equation is no longer valid once the distance is smaller than lambda. And finally, they will get smaller than lambda, and then the Navier-Stokes equation fails. Other physics applies, and the reality takes place. Yeah. Okay. Maybe just saying that the mean free path, actually this was already discovered, I mean, by Einstein, because, of course, Boltzmann was before Einstein. Yeah, he actually died in 1906, so just a year after. Maybe he didn't read the paper in between. So they were discussing about molecules and so on, but they had this theoretical concept, which was not accepted by the wider range of physics, also because they could not say how large a molecule is. So even though Einstein could not say how large the molecule is, but in that paper in 2005, he actually calculated what is the mean free path of a molecule, given the viscosity that we observe. Yeah? And so he had the first idea of the range of sizes that we speak about. Before that, it could be any number, and now he determined so it's in nanoscale. Yeah? Not picoscale, not microscale, but nanoscale. Yeah? So the mean free path in air under, so this depends on pressure and so on, under standard, pressure is about 16 nanometers. So now you can imagine when, so basically this distance defines for you when the Navier-Stokes equation is a good approximation or not in air, right? So for everything that's larger than 16 nanometers or much larger than 16 nanometers, which is many things in engineering, the Navier-Stokes equation is usually a good model. Yes, and let's also write this down. So Navier-Stokes is a very good for many engineering problems. So now briefly, before we come to an end, we come to the way that this is, okay, that's the background, and now we come to the lattice Boltzmann method that we use in virtual fluids, and most of this we'll do in the next lecture, but let's get started on this. So we have the lattice Boltzmann method. Often call this just LBM. Okay, so basically what we want to do is we only want to solve the Navier-Stokes equation. Yeah, so we don't want to solve the entire Boltzmann equation. And if we do this, all we need is solving the Boltzmann equation to first order in Knudsen number. If we have an approximation of the Boltzmann equation that is first order in Knudsen number, we are on the same accuracy level as the Navier-Stokes equation. So naturally, we'll end up solving the Navier-Stokes equation by that means. Yeah? So this is, of course, important because it simplifies what we have to do. The first order in Knudsen approximation of the Boltzmann equation, because this satisfies the this is sufficient to solve the Navier-Stokes equation. by so doing, we have a drastic simplification of the state space. Or, no, not the state space, the velocity space. Because what we have to do now is to find the discretization of the velocity space. Yeah? So we have to discretize everything. In the Navier-Stokes equation, we only have to discretize space and time. And in the Boltzmann equation, we also have to discretize space and time, but we also have to discretize the velocity space. So how do we discretize the velocity space? I'll describe this in 2 dimensions, even though virtual fluids only works in 3 dimensions. Now, there is a classification of these discretizations that is described as the DQ system, yeah, where you say we are in 2 dimensions, D2, and we use 9 speeds, Q9, D2, Q9. And you could draw this, let me see, you can draw this, okay, like this. So you're having 9 velocities. Say this here is our velocity in x, our microscopic velocity in x. This is the microscopic velocity in y. And so there would be positive, say there is a given value, say this is c and this is cc, then there would be minus c here. And say in x, c, and minus c, and so on. Yeah. So, and then there would be, for example, in this case here, there would be c and 0. So this would have 0 velocity in y direction. And in addition to this, we would have 0, 0 in the middle, non-moving. So basically, the simple model means that the velocity, right? I just try to write nicely. Velocity in each cardinal direction. Dyslexia is very annoying. So they are all chosen from the very small set. Namely, we could have velocity minus c, 0, and plus c. So if we are then in 3 dimensions, we have in 3 dimensions like in virtual fluids, that we have our velocity system from, say, this is x direction, and then we have this in y direction, and we also have it in z direction, and we have all the combinations of these. So how many are they? How are you with numbers? Combinatorics. So in 2D we have 9. Yeah. So we have 3 times 3. So we have 27 discrete. So this is how we discretize our infinite space yeah, with just 27 velocities. Now, why do we choose velocities with one static value? This is related to what we call the lattice versus the grid. So the lattice is the discretization in velocity space. And also we have a discretization in spatial space. Let's have it like this. So we have actually Cartesian grid here. And molecules will move from one location to another location, yeah? So this is now x, and this is y. And you see, if the velocities in each direction are always the same constant, what we can do is we can say that one particle is moving from this location to this location, from this location to this location, in a given time step. So we have a Cartesian grid with the grid spacing delta x, so this is delta x being equal to c times delta t, where delta t is our time step. Meaning that molecules hop from node to node. And that leads to a very simple so-called lattice Boltzmann equation. So now here we assume in this lattice Boltzmann equation, we assume that this population is, or that the particles are meeting at a collision time in this points here in the lattice nodes.
And you said it's happened when like the C is positive, right?
When the C is positive, okay, when if C is positive, it moves, for example, to the right, otherwise it moves, if it's negative, it moves to the left. Yeah? So, but what I was going to say here is that these populations, as we call them, the discretized F, yeah? So they undergo collision when they arrive at these nodes. And in between, they are located because they are moving with a given velocity, in between they are assumed to be halfway in between these nodes, at half time between these collisions. So this is, we write it down this way because later this leads to a lot of simplification. Yeah. So we assume that there is, okay, I'm now writing this in 3 dimensions. I indicate the direction in which a particle is moving with the 3 indices, I for x, j for y, and k for z. And then they are located at a position x, which is a lattice position, but they move about. So, and we describe them in a half time step, so time step in between, so at a time t plus delta t half, so they are somewhere in between two of these points, okay? So here this is x, y, z velocity indices. So this is now equal to, you see, this is x plus a velocity Cij delta x half. So it's going out from a lattice position further away, and it's at the next halfway to the next time step. So this is what comes out of the collision, so to speak. Now what is coming into the collision is the one that is, so to speak, upstream. Yeah. So now we go to the negative part. Delta t half, t minus, so, and this came there a time step before. So you see, this is a half time step after the collision, and this is half time step before the collision. So they are distinct by one time step, obviously. And this is, of course, not everything that is happening here, but here's also the collision happening. And this collision has to be multiplied with, because it's integrated, it has to be multiplied with delta t. And it's a collision on the population omega ij and k. And we call this here now, because this is what's going into the next collision, we call this the pre-collision state. Next time. And all of this together, which we can also write, so if we sum this up, we write this with an asterisk, and delta t half and t minus delta t half. So this is the post-collision state. So, and theCijk vector is the index I into the unit vectors k, the unit vector for z, and these are all unit vectors. Yeah.
So this, like in the first one, is like pre-collision when it's like going to this like the positive direction, right?
Yeah.
And then the second one is like.
No. The second one is not the one that's going in the other direction. It's going the same direction, but this is the previous. Okay, so.
It's the
previous state. Yeah, so
step.
from the previous time step, yeah.
Okay.
So the previous time step, you see, you just go one time step away, then this becomes this again.
Yes.
Yeah, but then there's the collision on top of this.
Okay.
So you have to add the collision to this. Yeah. So we are basically out of time. So I just write down a few more things, and then we'll continue next time. So it's very important that this is a very simple algorithm. And set up much simpler than you would have to do in solving the Navier-Stokes equation directly. So this is ideal for parallel computing. And because it's all linear, there's no need for iteration. As in, for example, the incompressible Navier-Stokes equation, which I now count like this. So I just write down two downsides. Maybe that is very stupid for me to end on a downside, yeah, but okay, so it's a downside, so it has to be said nabla. So there is no easy okay, I mean, I have to emphasize this. These are solved problems, but they are just not completely out of the box straightforward, right? So there is no easy use of unstructured grids, if you like these things. And the other thing is, it's all transient, which can be a good thing, but can also be a bad thing if you're interested in static flow conditions, yeah? So there is no, again, easy, there's also a solved problem, but it's not so straightforward. There's no easy way to compute steady states directly. Okay, and with this, I make a cut here. There's, of course, much more to say, but we'll have at least 2 more lectures on this. I'll now also end the recording.